So this series of videos, or I'm going to put them all together, is a series of tips and tricks of how to make solutions. And a lot of people have learned to do this in other labs, but you may have only figured this out from general chemistry, or it may have been a while. So I wanted to make this video to kind of help you get up to speed on how we make solutions. If you're asked to make a solution in the lab, the three ways that you'll be told to make a solution are: one, you might be asked to make a certain molarity solution. So I'm going to go over 5 molar ammonium acetate. You might be asked to make a percentage solution. So we'll go over 10% Triton. And then you might also be asked to make a dilution. So you might have a 20x solution, so like 20x SSC, and you may be asked to make 1x SSC. So this is kind of, you may have many other variations on this theme. So you may be asked to make a 1 molar magnesium chloride solution, or a 0.5 molar EDTA solution. But the math that we're going to go over pretty much works for everything. So first of all, you may be asked to make a 5 molar ammonium acetate solution. The two things that you need to know actually are: what volume do you need to make? So in this case, we're going to make 50 mLs. And you also need to know the molecular weight of the reagent that you are going to use. So if you go over to the chemical bench, or this ammonium acetate is actually in the fridge, if you look on the side of the bottle, there will be a molecular weight notation, and it will say either MW or FW, and it will give you a number. So on this bottle, it says FW 77.08. So that means that the molecular weight of this reagent is 77.08 grams per mole. So for ammonium acetate, then, we are going to say, all right, we want 5 moles per liter, and we want to make 50 milliliters, which is the same thing as 0.05 liters. You can write it out if you want to do it the long way. And that liter will cancel out with this. We also want to include the molecular weight, so we will say that this is 77.08 grams per mole. And the moles will cancel out. And you'll be left with 19.27 grams. So for this, if you add 19.27 grams of ammonium acetate, and in this case we're going to fill up to 50 mLs with RNase-free water, just because that's how we make this specific solution. You might fill this up with ultra-pure water if you're making something else. You can ask questions if you're not sure what water to use. And then that would make a 5 molar ammonium acetate solution. So I'll make a video of that in a moment. So that, if you were making any other solution, you had 1 molar of something else or whatever, you could change this math by changing the molarity, the volume if you need to make a liter instead of 50 mils, and of course replace the molecular weight with whatever else you're going to use for your solution. So that's how you would do the math for making a molar solution. You may also be asked to make a percentage solution. And so when you're dealing with percentages, you're either going to make a weight volume solution or a volume solution. And this has to do with whether the material you're using is a solid or a liquid. So for example, if you make a percentage solution of SDS in the lab, that's a powder, and so you'll use the weight volume formula. So that would be a little bit different. If you're doing a 10% solution and the material you're using is a liquid, then you can do volume to volume. So that means that 10% of whatever final volume you use will be this material. So for this, we're going to make 50 milliliters. And if we multiply that by 0.1. So what's 10% of 50 milliliters is 5 milliliters. And then of course we'll fill that up to 50 milliliters too. If you had weight volume instead, water is 1 gram per milliliter. So you would, instead of having 5 milliliters, you would use 5 grams of that powder and then bring that up to 50 milliliters if you had also a 10% weight volume solution. And then lastly, there are times when we have a 5x solution or a 20x solution and you're asked to make a dilution of that down to 1x. And so the way sometimes you can just do this in your head, but the other way to do this is C1V1 equals C2V2, concentration and volume. So if, for example, you wanted to make 1 liter of 1x SSC, and you were starting out with 20x, and you wanted to know what the volume would be, you would have, you would divide 1 liter by 20. So if you did all the math, you would, let's see, I'm doing the math in my head, so check my math. Would be 50 . Okay. So 1/20th of 1 liter is 50 milliliters. And so you would add 50 milliliters of a 20x solution and then fill it up with water to get 1 liter of a 1x solution. And you can also use this CV if you are not generating a molar solution from a powder, but if you're diluting it. So for example, another way to use this would be if you had, let's see, we often use 1 molar MgCl2, and if you wanted to know how much of that you needed to make a 0.035 molar, let's see, you're trying to make a 1 milliliter stock of 35 millimolar MgCl2. You need to make sure that the units match, so molar and molar. You can't have millimolar on one side and molar on the other. But you could solve here to figure out how much you would need to add of a 1 molar solution into 1 milliliter to make 35 millimolar. So you can write out that math too. But this formula you'll use a lot. So that's just the basics of how to make kind of where your starting point will be for making solutions in this lab. We probably make at least a dozen different things, so everything you make will be a little bit different in terms of the molecular weight, how much you need to make, whether you need to use RNase-free water or regular water. So make sure to ask questions about that if you're not sure about something. But I'm going to go through a couple of these examples so that you have a general starting point, and then you can build from there to make the other solutions we have in the lab. So the first thing we're going to make here is 5 molar ammonium acetate. Anytime you need to make just a small amount of a material, you can use a conical tube. So I'm going to make this 5 molar ammonium acetate in 50 mils. I've already done my calculation, so I know that I need to add 19.27 grams and then fill it up to 50 milliliters with RNase-free water. And I'm using RNase-free water here because this is something we use during RNA precipitation, so it needs to be RNase-free. So we have some weigh boats down here. I'm at the back chemical bench. Here's the scale. And right below the scale there are some weigh boats. So for example, you have 3 different sizes. They look like this. You'll put them on the scale and hit T for tare to make sure that it's zeroed. And then I've gotten out the ammonium acetate. I mentioned earlier in the video that there's a place where it gives you the molecular weight, so that's where I found that information. And I'm going to pour this out gently. So sometimes you'll pour out just a little more than you mean to, and what you can do is have another, take another weigh boat and just scoop out the extra and throw it in the trash. You don't want to take chemicals out of the bottle and then put them back in. There are also some spatulas that are over by the sink in the glassware cabinet, so if you prefer to use a spatula, you can do that. Just make sure you only use it once and then make sure that it's cleaned between uses. You don't want to contaminate chemicals with residue from other chemicals. So you want to be as precise as you can. The quality of your chemicals is going to determine how well a lot of your experiments will work. So you want to be pretty precise with measurements of this type. Once I have this measured out, I'm going to pour it into my tube. There's actually quite a lot of this, so I might even scoop part of it with the second weigh boat. And then I will show you how to fill it with water. All right, this is a very saturated solution, so there's quite a lot of this ammonium acetate in the bottle. I'm going to pour the Depsy or RNase-free water into the tube, and I'm going to get on eye level with it so I can make sure that I add the liquid right up to the 50 ml mark. And then I'm going to put this on the shaker so that the powder can go into solution. It'll take maybe an hour or two. You always want to make sure that you put the powder back right away, especially this one is one that's supposed to stay in the fridge, so you don't want to leave any cold reagents out. So this is a time when you're making solutions to always be cleaning up after yourself. You don't want to ruin a reagent by leaving it out. So I've just moved down the chemical bench just a little bit, and you can see I put that solution on to shake for a little while. And next we're going to make 10% solutions of Triton 100 and Tween 20. These are detergents and they're kept in bottles over here. It looks like this. And you'll notice that these are kind of like sticky, so detergent's like a soap. And we talked in the beginning about how to kind of measure out 10%. So if you're making 50 milliliters, you'll want to have 5 milliliters of this detergent to make a 10% solution. Normally, the most accurate way to measure 5 milliliters is to pipette, But because these solutions are these chemicals are so viscous, what I find is that if I try to pipette 5 milliliters, so much of it stays in the pipette that it's not actually as accurate as I would think. And so to me, I find the most accurate way to make these 10% detergent solutions is to pour 5 milliliters. So I have my Tween 20 here, and I have my conical, and I'm going to very carefully pour until I have 5 milliliters. And there's a line on the side of the tube that you can see 5 milliliters. I'm going to do the same thing for Triton in a separate tube. If you accidentally pour out too much, please don't pour those back into the bottle. You can just pour them out in the sink or pipette out a little bit of waste if you need to. And now I have Depsy water, which is RNase free, and I'm going to add to 50 milliliters for each one of these tubes. You'll notice I'm putting that right at eye level so I can see the liquid level really well. And so after these detergents have been added, you'll see that the detergent will be just still at the bottom. And these can be also placed on the shaker and allowed to shake either for a little while or overnight. And then you'll see that the solution has been well mixed and these will be ready to go. So earlier I made a 5 molar ammonium acetate solution and talked you through that. And now I'm going to use sterile filtration to sterilize that, that solution. So there are 2 ways to sterilize solutions. One is to use a filter system. So we have these Steri-Flips. We also have big bottles that have a sterile filter in it. And you're looking for something that has a 0.22 micron filter, and that filter has such tiny little holes that things like bacteria can't get through them. So that's one way to sterilize a solution. The other is to autoclave a solution, and I'll show you how to do that as well. But for ammonium acetate, we're going to use the sterile filtration. So I use this Steri-Flip, which is really good for when you have just one conical tube's worth of a solution. You can tear this open, being careful not to touch the filter with your hands. And this just has a tube with a filter on the top and then a little outlet for the vacuum. I'm going to take the lid off of this 5 molar ammonium acetate tube and just throw it in the trash and screw this Steri-Flip system on top of that tube. I'm then going to invert this tube and stick it in a rack. Now this outlet right here can stick to a tube, and I just have one of these pieces of tube. This is usually by my bench or by the bench across from me. And this can plug into a vacuum outlet. So I'm going to plug it in and then I'll show it to you. So here is my filtration system, and then the vacuum is back here with the tube between it. I'm going to turn on the vacuum, and that will pull my solution through this filter into the tube below. I made a mistake. I didn't get this quite lined up properly. And that will pull the solution down into the bottom tube. Once that liquid is through, you can remove this lid from the package, being careful not to touch the inside of the lid. You want to keep it sterile. That kind of defeats the purpose if you touch it with your hands. So when this finishes, I'm going to turn the vacuum off, remove the tube, and then remove the filter and the top tube and add this lid. You'll notice that then your tube is not labeled because you probably had the other lid labeled. So you need to relabel your tube. And once you have a solution that's been sterile filtered, as long as you follow sterile filter or sterile technique, then that solution should stay sterile for you. So this solution is almost filtered. So I'm going to turn off the vacuum. Remove the tubing. I'll have my, now you can see the liquid is in the bottom. I'm going to be very careful when I open this. I'm going to pull out the lid without touching the inside of it. And I'm going to screw off the filtration system and add the cap. So this is now my 5 molar solution of ammonium acetate, and it is sterile. So I'll label it and then it'll be ready to use. So we talked about generally how to make solutions, and we talked about using molar recipes to determine how much of things to add for a specific molarity of a specific chemical. So I'm going to go through one more complex example for you, and that is a solution we make called 10x PBS. It has 4 components. It's 1.37 molar NaCl, 27 millimolar KCl, 100 millimolar Na2HPO4, and 20 millimolar KH2PO4. So if you had a recipe like this where you have multiple things that need to go into a solution, you would do as we talked about before and look at the amount you want to make and the molecular weights to determine the mass to add. So for NaCl, we're going to make 1 liter. So we're going to multiply this by 1 liter. We are going to then use, so this, because this is molarity, this would be moles per liter. All of these would be 1 liter. A couple of those have millimolar instead of molar, so you're going to need to add in a conversion unit, which is 1,000 millimoles to 1 mole. Hope you can read that. And then use the molecular weight. So for example, this is 58.44 grams per mole. So when you solve this, you get 80.06 grams. Here, 74.55 grams per mole, which would equal 2.01 grams. Sorry, I'm running out of space here. And for the 100 millimolar solution, this is 141.96 grams per mole, which ends up being 14.196 grams. And this multiplied by 136.08 molecular weight grams per mole equals 2.72 grams. see if I can give you a little better view of this. This is just me solving for all of the different components of the 10x PBS recipe. So if you're ever having trouble with this, one of the recommendations I would make is just going ahead and crossing out all of the units to make sure you end up with grams as you should. You can do all of this math once and then keep a record of this in your lab notebook, or you can kind of get used to solving this multiple times. It's up to you. So what we're going to do now is to make this 10x PBS solution, and I'm going to tell you that the first things we're going to need out of the glassware cabinet are a beaker. So we're going to make our solutions when they are bigger than 50 milliliters in a beaker. And we're also going to need a bottle. This is where we will put the solution after we've made it. And finally, the last thing we'll need out of the glassware cabinet, which is over here, will be a graduated cylinder. There are some of those at the top, and I'll come and get that when we're ready for it. So the first thing we're going to do is set up for the solution and add these components to get this mixing. All right, so when we're going to make a solution, usually the first thing we need to add is the water. And we have this machine in the lab. This is the ultra pure water dispensing machine, and it can dispense water out of this part of the container or this little handle, which is usually pretty convenient. And so the first thing I'm going to do is dispense water. I said that we're going to make a liter, but you never want to go ahead and put that amount of water in the solution because you're going to add the powders and you're going to need some space to pH. So I often start out by adding somewhere around a little over half or 3/4 of the volume of liquid that I think I will need. And so now I'm going to walk back over to the chemical bench. I'm going to put this solution on a stir pad, and I'm going to go get a magnet. There are some magnets down below, I think. Sterilized down here. But there are also some in the glassware cabinet, so I'm going to go get one of those quickly. Okay, so now I'm at the chemical bench. I have a stir bar in my beaker, and I'm going to set it to start stirring. You want it to be stirring somewhat vigorously, but not having the stir bar knock around or anything like that. And so you'll have to kind of adjust the stir bar until you get a nice spin without it going too fast. I like it when it pulls a little bit of a vortex. That helps to mix things. And for this 10x PBS, I've written out my recipe. I have all of the components written down, and I'm going to start out by measuring out the 4 salts. So this PBS stands for phosphate buffered saline, and I'm going to measure out the 4 salts that I mentioned, the first of which is sodium chloride. And we have a really big container of sodium chloride. If you see that it has little chunks in it, you can shake it up. Some people like to use spatulas. My postdoctoral advisor hated spatulas because he always worried about contamination of one chemical to another. And so that was how I was trained more recently. There are some spatulas in the glassware cabinet. If you find that that is easier for you, just make sure it gets washed after each use. So I'm just going to shake this. I'm using the, using the scale. And I'm going to measure out my 80.06 grams of sodium chloride. I'm just kind of shaking it and tapping it to get close. I like for solutions to be pretty precise, so if I go a little bit over, I will take a little second wave out and remove a little of the the salts until I get right to the amount that I wanted. And then that can just be thrown away, any extra you have. So I have the 80.06 grams of sodium chloride, and I'm going to pour this into my beaker. Because I was looking at you, I got some of it into the foil that came with it, but you're not going to do that. You're going to get it all in there because you'll be looking where you're going. Every time you use a chemical, make sure that it gets returned to the shelf where it belongs. Some of our chemicals are supposed to stay at cool temperatures, and so those especially need to be handled with care. The second chemical we have is sodium chloride. I'm just going to use the same weigh boat for everything since everything's going into the same container. That's one reason why I wouldn't want to pour things back into the bottles, because then I could have contamination of one chemical into another. So the next thing I need is potassium chloride. So, you know, the protocol may have KCl, so another good thing to do is just make sure the bottles all have the chemical name that you're expecting. And when you're looking for the molecular weight, be extra careful that you grab the right bottle. I'll show you something that's going to be a little tricky with the next two. So I only need 2.01 grams. I'm going to remove a little extra. Another thing I will mention is that when you're using these scales, be sure to clean up after yourself. So if you have a spill anywhere, make sure you clean up very well. Okay, so that's my 2.01 grams potassium chloride. I'm going to pour that in. Going to turn up the stirring just a little bit. The next thing on my list to add is Na2HPO4. So we have two different sodium phosphate salts. I'm going to show both of them to you so you don't make a mistake. There is a sodium phosphate dibasic and sodium phosphate monobasic. And the same will be true of the potassium phosphates. There will be a monobasic and dibasic salt. And so you want to match up really carefully the chemical formula you have in front of you with the chemical that you're going to use. So I'm looking for Na2HPO4, and that is the sodium phosphate dibasic salt. The other one says NaH2PO4 instead of the reverse. So both when you're looking for the chemical to grab the molecular weight and when you're grabbing it to add to your solution, make sure that you grab the right one. So I need 14.196. This is a little bit more fluffy of a salt. Add a little extra. Again, it can feel a little wasteful to kind of pour out more than you need and have to get rid of it, so be careful not to add too much. This might be a reason why you should use a spatula. And I kind of like just tap my hand when I'm holding something. A lot of people will ask, how precise do you need to be? And my response to that is that probably within a range you would have a solution that you can use. But the more precise you can be with your solution making, the more reproducible your results will be. So if you always make everything exactly and precisely as it's written, then when you go to make this solution over and over again, you'll find that your results are the same. If one time you use 80.06 grams and the next time you use 81 and the next time you use 79.5, then every solution you make will be very slightly different. And if you have slightly different results, then we don't really know why, because we think every one of those batches you've made is 10x PBS. So the last component of the solution is KH2PO4, so potassium phosphate. And again, I'm going to make sure that I match up my chemical formula with what's on the bottle. So I need potassium phosphate monobasic, and I need just 2.72 grams. So when I get close, I'm just kind of tapping the bottle so I only get the amount that I want, or it comes out a little more slowly. Some of these will have a big chunk of salt in them, so you can always just shake them up if you need to break that up, or you can break them up with a spatula too. So I have that amount of my potassium phosphate. I'm going to pour that in, and then what you'll need to do once you've added the solid components to a buffer is allow them to stir until they've completely dissolved. There might be a couple of examples of solutions where that's not how you'll actually do it. The one example I can think of is half molar EDTA. That's a solution that you have to pH in order to get all of the powder dissolved. So you have to start the pHing process, which we'll go over next, in order to get all of the EDTA into solution. The other example that I can think of is 5 molar salts, 5 molar NaCl, which is a very saturated solution. And sometimes people will be making a salt solution and it just won't go into solution, and if it does that, you've set it too high. If you find that the salt hasn't dissolved after 20 or 30 minutes, you can add a little bit of water. So for example, I mentioned that we're well under 1 liter here. For a saturated salt solution where you're not going to pH or anything afterward, you may have to get closer to the final volume for all of the salt to dissolve. Occasionally, you can also speed along the process by adding heat. Be very careful when you're doing this, because that will affect different chemicals differently, and there are some chemicals that can be ruined by high heat. So for PBS, most of the solutions that we make in the lab, heat's not required. A saturated 5 molar NaCl solution might be the exception to that for the things that we make on a routine basis. So I'm going to allow this to spin, and I'll keep checking on it, and then we will come back and I'll show you how to pH the solution and how to bring it up to the final volume, and then how to treat it with a chemical called DEPC that will get rid of any RNases present. Okay, so I've watched my solution, or the salts in my solution dissolve, and I now have just stirring this 10x PBS solution that's gone all the way into solution. And the next thing we need to do is we're instructed to pH this to 7.4. And so we have a pH machine here. It's a black machine that's between the scale and the first stir plate. And when you come to it, what you'll want to do first is to calibrate it. And so you'll see that there's a little rack with 3 colored liquids. So this one will say pH 4, pH 7, which will be yellow, and pH 10, which will be blue. And you can go ahead and uncap those, but I would leave the caps on. You don't want to get them mixed up. And usually I just do a 2-point calibration unless I think something is wrong. So if I'm going to pH a solution that's between 7 and 10, I will use those as my 2-point calibration, but you can use all 3 if you want. when you're first starting out. If someone has used the pH meter pretty recently, it will probably be calibrated, but it's always good to check because you don't want to think you're pHing a solution correctly when you're actually pHing it incorrectly. So you'll see that there's a pH probe, and it will have a little bottle on the end of it. This is a little storage solution that keeps the probe in good working order. It's very tight, and so I would say that when you want to remove this bottle from the probe, what I would actually do is unscrew the bottle, carefully sit it on the counter, and then gently wiggle this lid off of the probe. I will say we have a plastic probe in the lab, but some of them are glass. We had a glass one that's broken, so just be careful, they're very fragile. You never want to let these probes stay out for very long, so what you want to do is pull this blue plug out and a little hole will open, and then you want to drop this probe into the pH 7 solution, being careful not to allow the hole to go under the surface. So I'm actually going to pour out a little bit of this because it's a little too full. Okay, so I have it sitting down in there, kind of resting against the side, and I'm going to go to the machine, and if I press F1, there's a little black bar above that that will say cal for calibration. So I'm going to hit F1 and hit start, which is F3. And you'll see that the pH level will start blinking as the machine measures the pH of the solution that the meter is in. And this should be pH 7, and what's blinking is 7.01, so it's very close. It was already pretty calibrated. Once there's a stable reading from the meter, the machine will say reading is stable, accept or enter buffer value, and you will hit accept. Okay, so the next thing you want to do is you never want to go from one solution to another without rinsing it. I actually should have rinsed it before I dropped it in the pH 7. So there will be a bottle of alga water, and there will be a container like this at the bench. And you can rinse the pH meter with the alga water, being careful not to shoot water into that little hole that's in the meter. And there should be chem wipes around that you can use to remove the excess water. And from there, you'll drop the meter into the pH 10 solution. I'm just going to put the cap on the pH 7 while I'm thinking about it. And I'm going to hit next, which will be F2 on the pH meter. And then I will hit start, which is F3. And then I'll have the same thing. There will be another line, P2, which is 0.2, and the pH is blinking at 10.04. And this should be pH 10, so that's pretty close. And this meter's pretty smart. It will know that you will be dropping it into 4, 7, or 10, and it will adjust whatever that reading is to the proper reading, so from 10.04 to 10. And so that has stopped blinking and says that the reading is stable, so I will hit accept. And that was F2. And then finally I'll have options that include calibration done, F3, and I will hit calibration done. And this will mean that the pH meter has been calibrated. Next, I want to go back to the measuring mode, and so I will hit F1, which says measure above it, and the meter will start measuring. So I'm going to rinse it off again since it's been in the pH 10 solution. I'm going to use the chem wipes again to wipe it down, and then I'm going to put this meter into the stand, which is, it's kind of an arm for the pH meter. And I'm going to adjust both the arm and my stir plate so that the meter is in the solution that I'm pHing. And depending on how things look, like actually I'm having a hard time getting the meter into the solution. So what you can also do is just tape the meter to the edge of the beaker. You want the end of the probe to be inside the solution, that way it can measure, but you don't want that end of the probe to be anywhere near the stir bar, because you don't want this to get knocked around, right? So you'll have to maybe play around a bit to see what works for you. I'm trying to adjust the cord to kind of hold it in place. I'm going to actually grab some tape to make sure that it doesn't come loose into the beaker. Okay, so I've now taped the meter, the probe, into the solution so that the probe is under the surface of the liquid but not near the stir bar. You don't want it to get banged around. And I'm going to, there's one kind of weird thing about this meter, which is you have to hit measure for it to measure. And it will, once you hit measure, there will be a blinking word saying stabilizing. And once that meter gets a stable reading, the blinking will stop and it will say ready, and it will give you a number. So this is reading as 6.68 and says ready. So because this is 6.68 and I need to pH this solution to 7.4, I need to add a base. And we have some solutions back here, including 5 normal HCl if you need an acid, 5 normal NaOH if you need a base. Those will be the ones that you'll use. These are strong acids and strong bases, so you want to practice really good chemical safety when you're using them. Be aware of where the eye wash station is in the shower, just in case you got this on you. And so we'll pH the solution. I will say I've already capped all of my pH solutions, and I'm going to put them back so that they don't spill. Okay, so over this bench, there are some glass Pasteur pipettes that look like this. And there are some little bulbs that will fit onto the end of the transfer pipette. So looks like this. It's a little bit easier to use glass pipettes for strong acids and strong bases, because those strong acids and strong bases can corrode plastic pretty easily. So now that I have that on, I'm keeping this side sterile, but I'm going to come over here and very carefully pipette some of this strong base into my solution. And I'm going to keep the lid on and work with the lid with my left hand and use my right hand to pipette. So I'm going to pipette some of the strong base. I'm not pipetting it yet, I'm just ready to go. I'm going to hit measure because I want this to be constantly measuring. And I have the solution still stirring. And I'm going to slowly add drops of this strong base into my solution. And so I've added a little bit, and the pH is up to 6.72. And I'm going to continue to slowly add the base until I get to 7.4. Make sure that this pH meter still has a blinking stabilizing label. If you see that the pH meter stops changing pH or says ready, then you need to hit measure again so that the pH meter will be actively measuring the pH of the solution as you titrate the pH. The other things I want to mention while I'm doing this, because this will take a minute, I've labeled this beaker. That may not be so important if you're just making one solution at a time, although you could run into a problem where someone else in the lab is also making a solution. But often you'll be making more than one thing at once. And you may think you'll remember that the solution on the left is this and the solution on the right is something else. But if you move something, then you may forget which is which and you would have to start over. So I always label the beaker before I start. I keep the beaker with the solution and then move the label to the bottle when I'm finished. So I'm at 7.04. One thing you should remember, you may recall in basic or general chemistry, that pHing it will not happen linearly when you have a buffer. So this is a phosphate buffer. So if you think to yourself, well, I added 10 droplets and it went up a certain amount, the pH changed a certain amount, that won't always be true. So at first it was changing pretty slowly and now it's changing more quickly. It's 7.22. So again, you want to make sure this is still saying stabilizing and changing as you add the strong base. Once you get closer to 7.4, which is where you're hoping to go, so I'm at 7.32, I'm going to slow down this process because it will take a minute for each droplet to fully diffuse into the solution and change the pH. So whereas at first I'm letting it go drop, 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 now I'm adding a drop and I'm letting it stabilize so that I make sure I don't overshoot my pH. If you were to overshoot, so say you were impatient, that's often a problem when we're making solutions. If you were impatient and you overshot and the pH was 7.45, you can often add a little bit of a strong acid to bring the pH back down. For PBS, that wouldn't be the end of the world. You could do that. I will say this, because I slowed down, it changed to ready. It actually stabilized all the way, so I needed to hit measure again before I added the next drop. There are some solutions that if you overshoot the pH, you can actually ruin them though. So I think it's a good practice to start being really careful and intentional about pHing solutions, going slowly, being as patient as you can. And this will help you to just be a better chemist when we're making solutions, so that you're more likely to have all of your solutions be correct. If you overshoot and overshoot and overshoot and overshoot, the pH may end up being okay, but you've added a lot of other ions as well, and that may actually alter a little bit of the properties of the buffer that you're making. So I'm pretty close at 7.38. It went to measure, so I'm going to, or it went to ready. So I'm trying to get it to measure again. Just one more droplet and see if I can get right at 7.4. Again, as I mentioned when I was talking about weighing the chemicals, the more precise you can be in your buffer making when it comes to pHing, the more reproducible your results will be. So if you make a solution that's supposed to be 7.4 and sometimes it's 7.39, 7.38, 7.42, then there could be subtle variations in your solution that could cause problems down the road. So I have a pH of 7.4. I'm going to remove this bulb and put it back on the shelf, and there's a medical waste, like a hard red plastic container over to the right that can be used to put this past your pipette in. It looks like this. So that's where we put sharp things like scalpels or breakable glasses. I'm going to put up my strong base, and now I'm finished with pHing this solution. So I'm going to carefully remove the tape. I'm going to take my probe over to the waste container and rinse it off again. You know, you don't want your solution to be contaminating the next person's work. I'm going to dry it off with the chem wipe. I'm going to replace the blue plug into the little hole that's on the meter. And then I'm going to take this little lid for the bottle and replace it. So you want to line this up so that once this is back in the bottle, the probe is under the level of the solution but doesn't go all the way to the bottom. And then I'm going to twist this bottle to put it back on. So when you leave this machine, you should leave the probe plugged, so that hole should be plugged, and it should be in the storage solution. leaving the probe to dry out can cause damage long term. Okay, so now I have my solution. It has the right components. It's been pH to the right pH. And the last thing I need to do is add water to bring it up to 1 liter. So as I mentioned, we start with a little bit less than 1 liter because we don't want to end up with 1.1 liters. And so I'm going to use a graduated cylinder, which is more accurate for volume, to pour the solution into. And then I will go fill it up with water to 1 liter. And it's okay if the magnet goes with it. So I'm going to go take this into the other room and fill it up to 1 liter with water. So now I've added ultra pure water from the blue and white machine. I should mention that the ultra pure water just has all of the ions and chemicals removed from it by filtration. So if you take water from the tap, it has many impurities. You can remove a lot of those to make deionized water, and then deionized water is polished further to make ultra pure water. So that's what we use for making solutions and as a base for our planarian salts too. So I have my solution up in 1 liter. Often people will ask, well, is the pH still the same? And you can check it if you want, but because water is neutral at 7, and because you're adding it to a buffer, and a strong buffer at that, that's concentrated, the pH is not likely to change very much. So I'm going to take my solution and put it into a 1 liter bottle. Usually we use these bottles for storage, and also we can sterilize these bottles by autoclaving. And I mentioned that you can leave the magnet in the graduated cylinder, and the reason for that is we actually want a magnet in our 1 liter bottle because of the next step I'm going to introduce to you. So I put the solution into the bottle. I'm going to take my label that I've already made that has my initials and date and what the solution is, and move it to the bottle. So now if you had lots of graduated cylinders going at once, you might even move the tape to the graduated cylinder and then to the bottle. That would probably be the most careful thing to do. So before you leave the space, make sure you've cleaned everything off. If you need to use some alga water or a chem wipe to wipe down the scale, that's fine. Sometimes you'll have powder from where you were weighing things out. You may have liquid from where you were pHing. You want to leave everything cleaner than you found it. You also may have chem wipes or tape or things like that that need to be thrown away. And if you need to refill the Elga bottle, you can use the ultra pure water. Elga is just another way we say that sometimes. You also want to clean your glassware. So these can be taken to the sink and just washed out with water and left on the brown tray that's right by the sink for glassware washing. And you can talk to us if you're interested in helping out with glassware washing and stuff like that. So both my graduated cylinder and my beaker are going to be washed. And then the last thing I'm going to do after I take care of that is to depth C treat my solution. And what I'm actually going to do is depth C treat both this PBS solution and also some water, and I will explain that to you in just a moment. So the next thing we want to do for these solutions, for the 10x PBS we made, and I'm also going to just treat some regular ultra pure water, is to depth C treat. And for many of the protocols we use in the lab, we want to maintain RNase-free conditions. So for work where we're doing an in situ and we have RNA riboprobes, or work with double-stranded RNA, we need the water to be RNase-free. And DEP-C or DEPC treatment can rid or inactivate any RNase enzymes that are present in a solution. So it's diethyl pyrocarbonate. This is a chemical that we keep in the refrigerator, and it's a chemical that's not very healthy, so we pipette this chemical in the chemical hood. And so what we will do is add this chemical to our solutions, to 10x PBS or to water, and we will add it at a 1 to 1,000 dilution, which is really easy to calculate. So if you have 1 liter, you add 1 microliter, or if you have 500 milliliters, then you add 500 microliters. And so I've already put my P1000 pipetter and my P1000 filter tips in the chemical hood, and I've also taken my bottles of 10x PBS and water, so just ultra pure water, to the chemical hood. And so what I will do is take you with me to go get the Dep C and take it to the hood so that we can add it to our solutions. So try not to make you too dizzy. My niece likes to walk around when she talks to people on the phone, and I almost need a Dramamine, so I'll try not to do that to you. So looking into the hood, there's a container like this that usually is sealed. If you push the button, it will open up. These are some hygroscopic chemicals that include diethyl pyrocarbonate. And that bottle is pretty empty, so I'm going to see if there's another one. There is. I'm going to take both of them. If we have more than one of something, try to use up the old chemical before going to the new one. So I'm going to take these 2 chemicals into the chemical bench for my Dep C treatment. So now you're in the chemical hood. In this chemical hood, I have my P1000, my tips, and these solutions. So this is my 10x PBS and then some bottles of water of different volumes. And I'm going to pipette this Dep C into each solution at that 1 to 1,000 ratio. I'm a little too tall for this hood, so I sort of have to adjust myself. This lid is not very easy. Maybe loosen the lids before you get your pipette. So you're going to keep this tip sterile. And I've already loosened the lids to my bottles too, so that I can just pipette that into the solution. That was all that was in the smaller bottle. We keep a bag in the back where you can put your spent pipette tips that have a less safe chemical on them. And one thing you'll notice when you add these chemicals, so I'm going to cap these. One thing you'll notice is that this Dep C is immiscible in water. So you might see these little blobs of the liquid not mixing with the water, but sort of floating around, kind of like oil and vinegar. And so what you want to do is cap these bottles tightly and then mix the Dep C with the water or with the solution. The reason you want to do this is so that the Dep C coats all the surfaces of the bottle. You don't want any RNases anywhere in the bottle, and so if you don't do this mixing step, there could be some that still survive the process. After you do this, you want to take the bottles and loosen the lids just a little bit, so not all the way off, but loose. So we'll do that for each of them. And then there are some stir plates in here in the chemical hood, so there's some stir plates in here, and you can put your solutions each on one of these stir plates. Try not to knock things over. And allow them to stir overnight. So you really want to do a couple of things when you set this up. You want to make sure that you loosen your lids. you want to make sure that you set this up to stir in such a way that it doesn't make a lot of noise for your colleagues who work over here on this side of the lab. So you want to try to be really careful with the speed. You want to make sure you don't turn on the heat for these because you don't want to heat things. And then you want to also make sure that you leave the light off in the chemical hood because the step C can be a little bit light sensitive. So as the step C incubates, it will degrade to ethanol. Might take you a minute to get everything stirring without making a lot of noise. And then you want to pull this shut. You're going to take your Dep C bottles back to the fridge right away. Take your pipette and pipette tips back to your bench. And then you'll leave this to stir with Dep C treatment overnight. So tomorrow what we will do, you know, after an overnight incubation, we will autoclave these solutions. That will cause evaporation of any ethanol that's come from the Dep C as it's degraded and get rid of it. So your solution won't have this chemical in it anymore after autoclaving, but it also won't have any active RNases in it. So that is the end of this part of the video. We're going to leave these to treat overnight, and then we'll talk about autoclaving tomorrow. Okay, so yesterday I had Dep C treated some solutions, and I had mentioned that Dep C treatment is one way that you can get rid of RNases in a solution. Today what we're going to do is to take those Dep C treated solutions and autoclave them, and that will serve two purposes. First, it will cause the evaporation and destruction of any of that Dep C chemical that's left present. And second, it will sterilize the solution. So if there are any stray microbes present in your water or PBS or any other solution you want to autoclave, the autoclave will use heat and pressure to kill those microbes. So elsewhere in this video, I cover sterile filtration. Sterile filtration and autoclaving are our best tools for making solutions and keeping them sterile. And autoclaving can be used for many solutions. There are a couple that are not appropriate, so detergents cannot be autoclaved. They're destroyed by high heat. And there are a few other chemicals in the laboratory that, because of their nature, cannot be autoclaved for sterilization. So if you want to sterilize a chemical by autoclaving, before you take everything to the autoclave, grab a pair of autoclave gloves. Grab one of these, this is like a little tub. There's several of them around the lab. You want to make sure it's one of these Nalgene tubs because this is resistant to heat and can be autoclaved safely. There are some plastics that will melt in the autoclave, so be careful not to do that. You want to also get all of your solutions ready for autoclaving. I will cap all of these solutions entirely until I get up to the autoclave, and then we'll vent them. You never want to autoclave something that's sealed all the way because the air in the bottle will expand as it's heated up and can explode the bottle. So you always want to make sure you give it about a half turn and leave the lid loose. But I always tighten the lids until I get to the autoclave and then check them all when I get there. The other thing you want to do is add some of this tape. So this is just a piece of autoclave tape. It has little stripes on it like this. And I put this on the lid or on anything else that I'm autoclaving to make sure that it is autoclaved. So after autoclaving, those stripes will turn black and let you know that the autoclave has worked. If there were some kind of malfunction in the autoclave, you would know because those stripes would not appear dark. Okay, so I'm going to go upstairs to the 6th floor with my tub and my gloves and my solutions. You can also autoclave dry materials like empty bottles, or we use the autoclave to sterilize our tips. So you can also use the autoclave to sterilize things that are not liquid solutions. So I'm going to take you up there to the 6th floor and we will run the autoclave. So I'm in the 6th floor autoclave room. It's really loud. It has 2 autoclaves, one here and one there, with a dishwasher in the middle. And so this is where we come to autoclave most of our stuff. I have gotten my bottles ready. So I've brought them up here and I've given them a little bit of a turn so that they're maybe half a turn from being totally closed. I'm going to put this tray into the autoclave and then show you how to autoclave. Okay, and there is my tray and my bottles. This can be very hot, so you want to use those autoclave gloves when you're putting things in and out of the autoclave. After you put in your solutions, and again, make sure your solutions or bottles have their caps slightly ajar, you're going to close the autoclave. And this one you close just by lifting up the door. And then if you go to the menu, it will give you a lot of different choices. So liquid cycles or gravity cycles, which is appropriate for glassware or other things that you want to sterilize. We have liquids, and you want to use a sterilization time that's about 10 minutes per liter. So I have 2.5 liters, so I'm going to use the 40-minute sterilization cycle for that reason. If I had just 1 liter or 2, I would use the 20-minute cycle. Giving me a second chance there. And then the autoclave will start. It will give you a time remaining, and you'll hear a really loud noise as it gets going. The other machine is a little bit different. So to close this machine, you need to use this pedal. And this screen is a little bit different. You would do cycle select, and you would have to choose the liquid cycle that's appropriate. So this would say sterilization temperature, sterilization time 30 minutes. So we could have used that one too. So when you come back to your autoclave, you'll see that it's finished, and it will say something like open door to unload chamber. You're just going to pull this door down. You might see some steam come out. And then you'll put on those orange fuzzy gloves like this and pull out your samples. Remember, they have the lids slightly uncapped, so you may want to either be really careful carrying this downstairs or else bring a cart. And then I usually let my solutions cool before sealing the caps. Otherwise, you'll actually create a vacuum so that when you open the bottles again, they will suck in air. And these solutions are now sterile. You can see on the lids there are darker lines on the tape. And these solutions, once they're cooled, can be ready to use.